Today we're going to discuss the origin of our own moon. Planet Earth is unusual in that it has an extremely large moon. The moon is roughly a quarter the size of Earth, and that's really big for a moon. If you look at the outer planets, for example, Jupiter and Saturn, they have a host of moons. But even though these planets are 1,000 times larger than the Earth, their moons are not 1,000 times larger than our moon. In fact, our moon is very big as far as moons go in the solar system. So this is interesting. We live on an interesting planet with an interesting satellite. Now, in order to understand the possibilities for where our moon came from, we first want to go through a rough sketch of the formation of the solar system. What is the framework in which the moon stands? So we begin by talking about matter. In general, there are three phases of matter that we'll discuss in this course. We talk about solids, liquids, and gas. Now, for something like H2O, you're all very familiar with those three phases of matter. Solid H2O is ice. In the liquid form, it's water, and in the gaseous form, steam. Steam is very low density compared to ice cubes or to water. And so that tells us that there's a correlation between the phase of the matter and how dense it is. The densest things tend to be solids, ice cubes, diamonds, rocks. Liquids like water tend to be less dense, and then lightest of all are the gases, such as the oxygen and nitrogen found in our own atmosphere, or those beautiful clouds that we saw above the mountains yesterday afternoon. Now, the next idea we want to talk about is energy. Everybody take your hands together and rub them against each other really fast. What's happening? Everybody's palms are getting really, really warm. So we've learned something here. We've been able to convert the energy of motion, moving our hands briskly against each other, to heat. Energy is a conserved quantity, by which I mean that we can change its form, we can move things to create heat, but it's always the same amount. So in a sense, something that's very high energy has particles with a lot of motion inside them. In the example I'm drawing here, we have a box with a few particles in it. So in the low energy phase, these particles aren't moving at all. They're grouped together. They're very densely packed, tightly packed together. They're very inert, means they're not moving, and they're cold. In the high energy phase, however, we have these little particles zipping around the box, literally pushing the box to be larger because they're pounding against the walls every time they bounce from one side to the other. So there's a lot of motion, and this is equivalent to having a cloud with a lot of heat inside it. Another way to think of this is to consider a classroom of kindergartners. When it's nap time, they're all quiet. You can pack them quite densely together onto a single rug and they all sleep. It's inert, it's cold, there's no motion. However, just after snack time, everybody is zipping around the room and you think the room just isn't big enough to hold them all. Their motion and their energy are literally pushing apart the walls of the schoolroom. So this is an analogy for how gas particles behave in a cloud, a gas cloud. When we look at a large cloud, it's just a group of hydrogen atoms in the universe, and they're packed together quite loosely because a cloud is just a very diffuse, low-density distribution of matter. This is how our own solar system began. It was a gigantic cloud composed primarily of hydrogen, the primary element found in our own universe. And over time, over billions and billions of years, something happened to this cloud. It cooled. Now, there's always a battle going on with a gas cloud. That's between the heat, or the energy that keeps the particles apart, and gravity, which is trying to compress everything into as small a volume as possible. So if you let the cloud radiate away energy, all the particles inside get more and more tired, they slow down, they stop moving around and resisting the gravitational force, and what happens to the cloud? It contracts, it's compressed, it becomes smaller, and smaller, and smaller, and smaller. And if you keep doing this for billions of years, we won't do this example in class, of course. If you were to keep doing this for billions of years, you'd eventually end up with a cloud that was so dense that you could form a star. Now, the next idea we want to talk about is angular momentum, or spin. So if you've ever seen the Olympics or anyone else playing around on ice, you'll notice that skaters like to spin in place, and if they start holding their arms far out from their sides, they spin pretty slowly. So that's the safe way to do it. But what do they do if they want to speed up? If they want to spin faster and faster and faster? They pull their arms inward to their body. So they compress their matter into as dense a column as possible, and then all of the energy of spinning is compressed into spinning that collimated, dense distribution of matter, and you go very quickly. It's a lot of work to spin if your arms are spread away from your sides. But once you pull your arms in, it's much easier. So that energy is used more efficiently. The net result is that you spin very, very quickly in place. So a denser, more concentrated distribution of mass spins much faster. Now, if this is true for human beings, it's also true for gigantic clouds of hydrogen gas in the early universe. So our cloud starts out as a big diffuse cloud, and inevitably it's spinning a little bit in some direction. That's because nothing is ever formed perfectly. There's no such thing as a completely still at rest object. To verify this, take a ball and just start playing with it. So you throw it from hand to hand, over and back and forth, and you notice it's always spinning a little bit. It's very hard to take a ball, to throw it up in the air, and have it just go up and down, but not spin at all. And that same thing is true in the universe. Clouds inevitably are spinning a little bit to the left, or a little bit to the right, a little forward, or a little backward. There's always some net angular momentum, a little bit of spin in the system. Now, as the cloud cools, that spin doesn't go away. And as the mass gets denser and denser and denser and clumps to the center, that's like an ice skater pulling their arms into their body. The result is that the cloud, when it becomes very dense, is spinning quite quickly. And that is the energy that has our planets rotating around the sun today. So the matter collapses into a disk. It has a preferred angle, some direction it's spinning in, and then you find a large concentration of mass in the center. That makes up the sun. And then all the planets and satellites and comets and asteroids are grouped around that in a thick disk of material, which is spinning. It contains all of the little spinning energy of the initial distribution of particles, all crammed together. So with that rough picture of the solar system's formation, we now want to talk about the origin of the moon itself. Now, the planets formed out of this large disk, and they tended to form in place. So if you ever looked at the distribution of the planets, we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. Yes, we're still counting Pluto. And you see that there's a bit of a spacing. No planet runs into another planet. And the reason for that is that the planets formed out of the material in concentric rings placed around the sun. If we look at the orbit of the Earth, for example, early on in the solar system, there were just lots and lots and lots of rocks spread throughout our orbital ring. And over time, those rocks would run into each other as they orbited the sun. And rocks are sticky, so they tend to stick together. So the rocks are orbiting around, and one pushes another, nudges a little one, this sort of thing, and they run into each other. And the small ones end up sticking to the big one. And as the bigger rocks become larger and larger, what happens? They become gravitationally attractive. So pretty soon, things are running into them and sticking, and then things are also being drawn towards them. So you end up with these large bodies, which are the protoplanets, the planets in the early stages of formation. And now the moon is an interesting satellite because it has enough mass to count as a planet if it had a different orbit, perhaps. So the question is, how did we end up with such a large moon? What is the origin of the system? Now, there are four key possibilities for the formation of the moon. One is that it's a planet, just like Earth, and it passed a little too close to the Earth. It was caught in the gravitational attraction of Earth, and now it orbits around us as we both orbit around the sun. A second idea is that the moon is a captured asteroid. Now, an asteroid is just a fancy word for rock. There are a huge number of rocks in the solar system. You find a lot of them in the gap between planet Mars and planet Jupiter. We call that the asteroid belt, because if you look all the way around the sun, there's just rocks, 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 forming this gigantic ring. A huge number of them are less than a kilometer in size. A few of them are more than 100 kilometers in size. So that's the distribution of sizes of asteroids. And the moon would be a very large asteroid if it were an asteroid. So this is a possibility. Perhaps the moon used to orbit a bit further out in the solar system, but it wandered in and then again was caught by the gravity of the Earth, and now it orbits us. A third idea is that the moon is actually a spun-off fragment of Earth. So if in the distant past the Earth was spinning much faster than it is today, so we didn't have a day cycle of 24 hours, we had a day that was much, 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 much shorter, it might be that some of the material would actually break away from the Earth because of all that spin, all of that energy of rotation. Fourth idea is that early in the history of the solar system, things were a mess. There were no stoplights, there were no traffic lights, particles, planets, protoplanets, asteroids, everything was running in different directions, and many of them were colliding with each other. So what would happen if a forming Earth was run into, a sort of hit-and-run accident, by something roughly the size of Mars? Not something so big that the Earth would be destroyed, but not so tiny that we could ignore it, the way we ignore the meteors, which are constantly coming into our atmosphere. what would happen? I'm going to show you a quick film, and we're going to see actually a computer model of this process. So here we have a simulation of a giant impact. The impactor, this is the roughly Mars-sized planet, comes in. Earth is sitting there innocently, waiting, and then kapow! You get a big impact. For the first 8 frames here, we see that impact. Then we jump down here, and then we have the last 8 frames. And here what we're seeing is the response of the Earth to this impact. Now we don't see the moon here. The moon would be a lot smaller, and this simulation doesn't actually contain the formation of the moon. But what you do see is that there's a ring of material around the Earth in frame 16, which is thrown up around it. That's the material which will form the moon. So that material slowly cools and coalesces. Again, rocks are sticky, so all the rocks stick together, and the result is that we end up with a very large satellite as a result of this collision. That's our 4th hypothesis. Now, in order to evaluate and compare these 4 hypotheses, we want to look at certain properties of the Earth-Moon system. The first is the ratio of oxygen isotopes on the moon versus the Earth or other planets. The second is whether the moon has an iron core. And the third is whether the moon had ever melted at some time in the past. Melting just means everything gets so hot that it moves around freely. And the result of that is that the densest materials end up in the center of the planet and the lightest materials end up on the outside. Our planet, for example, has melted or differentiated. We know that because we have the light, earthy mantle on which we live, on the crust, on the outside, and then deep in the center of the planet we have the dense metallic iron core. So this is the process of differentiation. Densest materials fall to the center of the planet, light materials stay on the outside. And in order for things to move freely like that, everything has to melt. We have to have things hot enough that they can slip and slide and move around each other. Now, let's examine the case of the moon. One very interesting fact about the moon is that when we study the ratio of various oxygen isotopes, different types of oxygen on the moon, we find that they're almost identical to those found on the Earth. Now, this is like fingerprinting. If you're out investigating a series of burglaries and you find the same fingerprints in every house, you begin to get a little suspicious, and you think, this is one person robbing house after house after house, not 6 different people who simultaneously get the same idea. The same thing is true if we look at the Earth and the moon. Now, an isotope is just a fancy way to say an oxygen atom with a certain number of neutrons. Conventional oxygen has 8 protons and 8 neutrons, but you can also have an extra neutron within the nucleus of the atom. So if we look at the ratio of those, how much slightly different oxygen is present, we can tell something about where matter formed. Now, the fact that the Earth and the moon ratios agree so precisely tells us that they must have formed out of the same material. It would be extremely unlikely if the moon formed way on the other side of the solar system, and yet it had exactly the same properties as Earth. That just isn't probable. So the fact that they have the same oxygen indicators tells us that the moon formed out of the same stuff that the Earth did. That's one piece of data. The second question is whether the moon has an iron core. Now, the moon does not have much of an iron core, if it has any at all. If we measure the density of Earth, we know that's about 5 grams per cubic centimeter, whereas the density of the moon is 3 grams per cubic centimeter, considerably lighter. And the main reason for this is that there's not a big, heavy iron core in the center of the moon. Our third question is whether the moon materials melted at some time in the past, whether they were differentiated, whether the densest materials ended up in the center of the satellite. And indeed, we see that this did happen for the moon. Sometime in the past, the moon was really, really hot. So hot that the dense, heavy metals were able to ooze their way to the center of the moon. Now let's look at our 4 hypotheses again. Our first hypothesis is that the moon was a sister planet to Earth. This hypothesis has a big problem, and that is that the core of the moon does not have enough iron. If the moon were a planet that formed the same way that Earth did, it would have a fairly heavy central core, and then it would have accreted lots and lots of rocks on the outside of that. The moon does not have a big core. So that says that it's not just a small planet that happens to form next to us. If the 2 planets form together, that would explain having very similar oxygen ratios, but it would not explain the lack of iron in the core of the moon. So this hypothesis is no longer terribly strong. Our next hypothesis is that the moon is a captured asteroid, something that used to be much further out in the solar system. It slowly wandered into the center of the solar system and then was captured by the gravity of Earth. And the big problem with this hypothesis is that there's no way to explain why the moon would have the same oxygen isotope ratios that are found on Earth. The moon must have formed somewhere near to the Earth in order to explain that piece of data. So anything that wanders from a great distance inward is not going to have that good agreement. So again, we don't believe that the moon is a captured asteroid. However, other moons can be captured asteroids. The moons of Mars, for example, Phobos and Deimos, both look as if they are asteroids, and we think that they probably, in fact, did come from the asteroid belt. Our third hypothesis, this is a very engaging one, is that the moon is a fragment of the Earth. It was spun off at some time in the past. And this is a great idea. I love the idea of Earth spinning so fast that it just breaks apart and a piece breaks off and flies up into the sky, but unfortunately it's not tenable. There's one really big problem with this. In order for the Earth to break apart, it has to spin very, very fast. And even accounting for the fact that it would slow down over time, if that were the case, we would now be spinning so fast that each day for us would last only 2 hours. And we know that's not true. So we would have to be going very, very quickly. There's just no way that the Earth could have discarded that much angular momentum, that much spin over its lifetime. So unfortunately, this very exciting hypothesis again doesn't match the data. That leaves us with one final hypothesis, and this is that the moon is a relic of a catastrophic collision early on in the solar system. And we believe that this is the strongest hypothesis to date. What we think happened is that the Earth, forming Earth, was moving along in its orbit, and then something about the size of Mars came along and collided with it early in the solar system. So two protoplanets collided. We're not saying it was Mars itself. More likely, it's an early planet that didn't survive and is now not one of our planets that exist today. This object collided with the Earth, and the result that was a lot of material was broken off of the Earth and thrown up into orbit around. Because we had a big explosion, we had a lot of energy released, that material was hot. And that's very important because it means that that material was allowed to melt. All that material formed a loose ring around the Earth, and then over time things stuck together and lumped together and stuck together, and so slowly they formed into one big lump, which became the moon. Because of all the heat of the impact, that material was able to melt, which means that what iron was available was able to seep to the center. So in this fashion, we end up with molten materials. We have differentiation, where the densest things move to the center. We have a small amount of iron thrown up by the impact, but since the core of the Earth is where the iron tends to be found, we don't have a huge amount of iron to deal with. And then very importantly, by building the moon out of material taken from the Earth, we're able to have identical oxygen isotope ratios to those found on the Earth. So this hypothesis can explain all of the key observables, the data points that we have about the origin of the moon. And therefore, it's the best one in town. We're going to go with it. So this is how we think that the moon formed. One big crash, one hit and run, and the result for us is a beautiful satellite in orbit around us. We've talked about gravity several times today, most importantly when we said that a small body which passed too close to a planet might be captured by its gravitational field and fall into orbit around it. We know that many of the moons of the outer planets are probably asteroids which were accreted this way, and it's possible that the two small moons of Mars came originally from beyond its orbit, from the asteroid belt. Let's now talk a bit about the basic idea of gravity. Gravity is a fundamental force that acts throughout the universe. It's an attractive force because it brings things closer together. Every piece of matter in the universe is attracted to every other piece because of gravity, and the more massive an object is, the more strongly it attracts its surrounding objects to it. Gravity also acts more strongly upon nearby objects than more distant ones, which is why our neighbor, the moon, orbits around us, the Earth, even though the sun is more massive than the Earth. If you place the moon halfway between the sun and the Earth, it would be drawn more strongly toward the sun. But because it lies a mere 384,000 kilometers above our surface, and the sun is a good 150 million kilometers away, the moon's not going anywhere. This is what poets call job security. Someone has to rhyme the raccoon in the moon with a wedding spoon in June. So, gravity is proportional to mass and inversely proportional to distance. We can write this as an equation, and in fact we've done so on the web page. F equals big G times the product of m1 and m2 divided by r squared. So what does all that mean? F stands for force, in this case the gravitational force between two objects. Big G is the gravitational constant, a number which never varies. This is one of the defining constants of our universe, like the speed of light, how quickly photons can travel in a vacuum, or E, the charge of the electron, or the fine structure constant, alpha, which governs the strength of electromagnetic interaction. If any of these values changed, we'd be changing the structure and form of the universe itself. So if you had a knob and you turned up the value of G, it would become a lot more work to stand up and walk around while fighting the gravitational field of the Earth. Forget climbing stairs. Someone would have to make the coffee constant stronger as well to compensate, or else no one would ever get out of bed in the mornings anymore. Our next term is m1 times m2, and this is just the product of the masses of the two bodies. We then divide this by the square of r, the distance between the two objects. We can say that there's a simple scaling relationship between mass and distance in the force equation. If, for example, we doubled the mass of the Sun, then everything else in the solar system would be drawn towards it twice as much. And if we shifted the Earth to lie 10 times further away from the Sun, the force would decrease by how much? That's right, by a factor of 100, because the force is inversely proportional to the square of the distance. 10 squared, 100. Let's now introduce the concept of acceleration. Acceleration is the rate of change, in this case, the rate at which your speed increases as you are drawn towards another body. You've probably heard that when you drop an object here on the surface of the Earth, it falls and it accelerates at 980 centimeters per second squared, or 32 feet per second squared. That's the local gravitational acceleration. And how does this relate to the gravitational force? We say that F equals m times a, or force is equal to mass times acceleration. It can be more useful sometimes to consider acceleration rather than force. Because the equation for gravitational force contains a mass term already, we can re-express it in terms of acceleration and cancel a mass term. We know that there is a gravitational force of attraction between you and the Earth, but we also know that if you step off a high diving board, you fall toward the Earth rather than the whole Earth falling up to you. The reason is simple. The acceleration that you feel pulling you towards the center of the Earth is big G times the mass of the Earth divided by your separation. The acceleration that the Earth feels pulling it towards you is big G times your mass divided by your separation. So because the Earth is so much more massive than you are pulled down to its surface. We can say that the force indicates how much you are being pulled, but the acceleration tells you how much you move in response to that pull. The net gravitational force is just the sum of the gravitational attractions from all bodies. So for example, if you and a friend are situated on opposite sides of the Earth, then you will both experience the same net force pulling you towards the center of the Earth. And if you were on the surface and your friend were placed high above the Earth in orbit, your friend on a spacecraft would feel less of a pull toward the center of the Earth because they were further away from it. Let's talk for a minute about the difference between weight and mass. The mass of an object is merely the sum of its matter, the amount of stuff that it contains. And this doesn't change with location. Its weight, however, does depend on location. Weight is just another way to measure the local gravitational force, the object's mass times its acceleration. Let's say you hop on the scale at home and you weigh 120 pounds. That 120 pounds is the product of your mass times the gravitational force at the surface of the Earth, 980 centimeters per second squared. But what if you took a vacation on the moon? Because the moon is much smaller than the Earth, the gravitational force there is a factor of 6 less. Your mass would be unchanged, assuming you didn't eat too many peanuts on the flight, but your weight would now be only your mass times 1/6 as great an acceleration, or 20 pounds. How could we change the gravitational force experienced at the surface of the Earth? One way would be to change the density of the Earth, the mass per unit volume. If we replaced all of the metals and dirt that make up the volume of the Earth with an equivalently sized sphere of down comforters and cotton candy, we could keep it the same size but lower its mass tremendously, and the gravitational force that it exerted would drop. If we replaced the Earth instead with materials from a white dwarf, almost 1,000,000 times denser than the Sun, then of course the gravitational force would grow inconveniently large.